So before I start, I'd like to acknowledge the contributions from my research group. So you can see the names here. And all I want to say is that if I was tasked to take a crew on another planet, I would take all these people with me on the ship. I wouldn't go to explore another planet without them. And apart from my research group, I'd like to acknowledge contributions from or support, continuing support from these Australian-based national science, national computational infrastructure, and Australian Research Government Research Council, which is equivalent to European Research Council. And finally, OSCOPE, which is probably the best comparison is with the EarthScope in the United States. Okay, so I guess I have to stand closer to here for this to work. Yes, so I also would like to thank the organizers, particularly to Pierre, who could have probably delivered this talk, although from a slightly different perspective. And I feel a bit more relaxed because I have more time. So there's a little time to introduce the research group and where I'm coming from. So some of you have been to Canberra. This is a Research School of Earth Sciences. We recently restructured the school, and maybe you recognize some name here of the continuing faculty. Apart from that, we have 15 early career researchers and 25 PhD students, so altogether about 60 people in the geophysics area. Then the Australian Research or Australian National University is the main research university in Australia. In particular, it's attracting students for education through research, and that's the main idea of the ANU. In terms of my own research group, this is how it developed over years. So you can see a quite international group, and maybe you even recognize there's at least one French here. It's a Benoit from Lyon. And this is how we look today. So this is more like more recent, 2022 and 2023. In terms of our research interests, they are aligned with my research interests from the PhD times, and when I started my romance with the inner core, and I still do that. But you can see, moving to another continent, to Australia, of course you are much closer to Antarctica, you're closer to the Southern Ocean, and you have access to these remote areas of the continent. So I use it to really promote the proliferation in the remote areas, and this is for the benefit of the global seismology. But in today's talk, we will focus on the Earth's correlation wavefield, although you will see the flavor of some of these other components. So this is the online and goals of this lecture. First part will be on the introduction, and I really want to give you a good flavor why we in the global seismology community, especially in the deep Earth community, why we need tools like a Coda Correlation to make further advances. Secondly, I will then introduce what I mean by earthquake Coda Correlation wavefield. You will see slightly different definitions, maybe more from the qualitative point of view, because we've seen some mathematical formalism for Coda correlation. And finally, I will show you some applications, in particular how we can probe the interior of the Earth and other planets with the Coda correlation. And I hope I will demonstrate that this is really the way forward in the decades that are coming, that are in front of us. Okay, so in terms of the motivation, there's a slight delay with this. I'm a little bit struggling but hopefully it will work here. This is very basic. I really don't need to spend too much time on this, but in a high frequency approximation, when it comes to the deep Earth, then you can see we use the so-called PK-IKP waves that traverse the Earth's inner core, and a few other branches that sample only the outer core. And then we also use the waves that reflect off the boundaries. So you can see here PK little IKP, and you can see some of these other more exotic arrivals or more exotic seismic phases. So then we have here, it's a good time to show you this historical seismogram. It's 100 years old, recorded in Berkeley, the first station in the Western Hemisphere. So it's a regional earthquake here, and you can see standard arrivals of P waves and S waves and some surface waves. And typically what seismologists do then, we pick phases, we pick arrivals on these seismograms. And here's an example of a bit more exotic group of arrivals. So this is the core of the Earth. And this is just a sketch, and you can see how some of these reverberate through the outer core multiple times. So this is an example of P4 KP and P7 KP from the Cold War era. So these are from the Novaya Zemlya explosions recorded in California. So some of us use standard arrivals. We heard the term ballistic many times during this symposium, but we also use some of the exotic phases, such as the multiply reverberating waves in the Earth's core. Then we pick these arrivals, like it's shown here. On the horizontal axis is the epicentral distance, on the vertical is time. And if you do this a million times, you can get this sort of representation, this beautiful travel time section with each seismic wave shown here in different color. And then by the virtue of geophysical inference or geophysical inverse theory, so you can go from here to here, of course. We can give one full seminar course on this, how this is done, but you can see here the main features, for example, the Earth's core, and you can see here the green line, which is shear waves, do not propagate through the outer core. And so this is PREM, of course, from the long period waves. But if we have done everything correctly, then we can go in the reverse mode. We can then go in the forward mode from here back to here, and you can see that if you have a resemblance of the observations, this means you have done something well with your geophysical inference. Okay, but I said I will give you good motivation for the Coda correlation wavefield, and this is why I have a little time to talk about the inverse theory here. What it means, and you're all familiar in the geophysics. It's basically you start with a model. I chose here the inner core, so it can be anything. It can be travel times or anisotropy in the inner core, and then through a forward way from that model, we can calculate the model predictions. We compare them with the observations. If we are happy, we accept it. If we are not happy, we go through another iteration, and so on. So this is, we can think of this as a forward problem or a deductive way of getting results, and this is inductive. And then inner core here could be seen as a black box that you fill with the information. And again, here I'm showing you an example of what that means in practice. So when it comes to the inner core, we can come up with all these different models of inner core anisotropy. And the anisotropy here refers to cylindrical anisotropy, which is a first order observation where the waves that propagate along the Earth's rotation axis move faster through the inner core than those in the equatorial planes. But the bottom line is that people come up with these models Each one of them was published in probably high profile journal, and you can see how different they are. So that this non-uniqueness is the devil that we have to deal with. It's a known devil in geophysics, right? So you can see how almost the same data set can lead to all these different models, and it explains a part of the data, but the important distinction is that it's not required by the data. Okay, so how do we deal with this non-uniqueness? Here I propose an all-embracing approach where we as seismologists absolutely have to work with geodynamicists and high-pressure mineral physicists, and there are all these other disciplines that contribute to our knowledge of the deep Earth, in this case, the core of the Earth. So in Australia, we have done our part, and I mentioned the proliferation of seismic instruments. And here I just want to show you a few examples from the field work. You can see Australia is dominated by the red color. It's more similar to Mars than the rest of the Earth. It's all oxidized rocks there. Some places you go, it's pretty much stepping on the fossil. Everything is older than 3 billion years. In the western part of Australia, for example. And what we usually do, we go to the field with a small group of people, the two vehicles like this, and then we dig an instrument. This is a sensor that then records continuously for 1 or 2 years. So of course we have to maintain these instruments, we protect them from the wild animals and so on, and we collect data, and we have to explain to the farmers that we are not there to look for the oil or ore, but that we are really interested in these teleseismic arrivals, Australia being like a perfect natural lab surrounded by earthquakes that we can use to understand the evolution of the continent, but also to look in the deeper parts of our planet. And then here's another example. In particular, we have well covered the southeastern portion of Australia, and Nick Rawlinson here, who is now professor at University of Cambridge, almost single-handedly installed many of these stations in the southeastern part of Australia. A few more pictures here. If you're wondering, a few people ask me, what's the most dangerous thing in Australia? Snakes or spiders, of course. But you can see that we have the camels. I don't know how many of you know that camels were imported from Saudi Arabia for transportation. And there are so many of them today when you go to a field like this that Australia basically exports them back to Saudi Arabia these days. So you can see everything dominated by red. We even have some accommodation underground in a few places because it's so hot. This is a Coober PD where Mad Max was filmed, for some of you who know Mad Max. Anyway, so these are beautiful pictures, of course. Here's Anja Redding, who also contributed to many of these experiments. And our curiosity takes us away from the continent, and here's an example due to the vicinity of Australia with Antarctica. This is a work we started with Tan Son Pham, who is here with us today. We applied the autocorrelation to study the properties of the Antarctica ice. And we were quite successful with that because autocorrelation turned out to work really well when you have such a high impedance contrast between the ice that's sitting on the top and the solid Earth. And we compared our results here with the radio echo sounding, and you can see here it matches really well. So this presents a new and I would say a much cheaper method to study the ice properties in Antarctica in comparison with the radio echo sounding, for example. And then we expanded that to also look at the structures where you have a ice shelves. So you can see here another added complexity is you have a water layer between the solid earth and the ice, and that worked really well as well. But you can think of this autocorrelation as really an introduction to cross-correlation that I will show. And of course, you know, I said our curiosity took us to Antarctica, but it will also take us to these icy planets. And hopefully the methods that we collectively design and invent will be used one day on these icy planets' surfaces. Okay, so here I want to show you what my group in particular has been doing in the last decade or so with these arrays in Australia. These are short aperture arrays, but they are logarithmic spiral arrays in the sense that there's a configuration of elements with the 3 spirals, and it has a very good property that it suppresses the side lobes of the incoming energy. And here you can see this is a classical linear shape array in Warramanga, which is a monitoring facility in the Northern Territory. And this is how spiral array can observe the same wave field in comparison. So you can see that with the less elements and this particular configuration of arrays, we can achieve a much better control over back azimuth and the slowness than with the classical linear arrays. So we installed a few of these in the interior of the Australian continent, and then we went to the Southern Ocean. This was the first Australia-led OBS experiment near this location here, Macquarie Ridge, which is of course the boundary between between Australian plate and the Pacific plate. And we proposed this configuration, which at the end, in practice, didn't look exactly like this, but we resembled it. That's of course based on the conditions that you have in the field. And you can see here again the spiral array in the south and this classical X-shaped array in the north. And here are some pictures from that voyage. And the first observation was interestingly not something related to large earthquakes, because we went there to understand some of the largest underwater strike-slip events on Earth. In fact, the largest underwater strike-slip events in the 20th century and the 21st century happened here. We think that because of the oblique component of the source of these events, they might hold the key to our understanding of whether there is an incipient subduction happening in this area or not. But the first observation, and this is made by a sonar of our ship. First of all, I should say we all got seasick, and it was not, a voyage where, I thought naively that you will go there and there will be few perfect storm events during that month. And then there will be some calm periods. But when you go to the furious 50s, you're exposed to 5 to 10 meter waves constantly for 1 month. So it's like walking on some wooden legs and balancing all the time. So it's really an extreme geophysics to go there, try to do something in the most extreme topography on the planet. So this is the steepest topography. With the rise from the ocean floor to the top of this island, 6 kilometers in less than 40 kilometers laterally. There's no such place, right, on Earth. So in these conditions, we installed these OBSs. But what I wanted to say is that the first image revealed that there's evidence for these really huge landslides, underwater landslides that are probably, so this is just to give you an idea, this is 35 kilometers long, so this is about a few hundred kilometers. And on both flanks of this ridge, you see the evidence for huge mass wasting events that are probably responsible for some of the historical tsunamis. Okay, so going to the field, installing all these stations and networks, and we have seen good examples of really dense networks that were installed. You can boost, what we know about the deep Earth, and this is a classical research where, when it comes to the inner core, where we added a few networks in relatively exotic location, in the sense that these data were not included in the catalogs before. So this is Thailand and Brazil. And we studied these antipodal PK-IKP waves that sample through the center of the planet, really. And when you plot the travel time residuals with respect to the predictions from the one spherically symmetric models of the Earth, then you can see this very well-known trend that for the polar paths through the inner core, you have in this case, these are absolute travel times, so you have some advance, and then these are the equatorial. So this angle here is the angle between the Earth's rotation axis and the path in the inner core. So for very polar paths, we have up to 6 seconds advance in comparison with equatorial paths, which is a kind of what the model predicts. And by doing this, we studied the very center of the inner core, and we were able to confirm the existence of the innermost inner core. The innermost inner core, for those of you who are less familiar with this, is the transition from the rest of the inner core to the innermost inner core is not the first order discontinuity, right, that we have in other examples. For example, core mental boundary or crust mental boundary. But it's more subtle. It's a change in the anisotropic properties of the inner core. So in particular, what I mean by that is that the innermost part of the inner core, the slowest part of the PK-IKP waves, is in oblique angle, right, with the rotation axis. So we find here about 60 degrees, right? Whereas at the rest of the inner core, the slowest parts are in the equatorial plane. So that subtle difference between the slowest axis of anisotropy defines the innermost inner core, which, by the way, was proposed back in 2002 by Ishii and Javonsky. And further to that, take this dense array in Alaska that we have, which is shown here, and this earthquake. In this study, by using again the expansion of seismic data, we were able for the first time in the history of modern seismology to observe these multiple reverberations through the center. I'm not talking about 2 times, but really 4 times, 5 times, and so on. And I will show some examples of that. It's great to see that this of course, attracted the attention of the global community, and particularly journalists who are interested in this. So we call these ricochet waves. And so that ended up on the front pages of famous newspapers. And here are a few examples. This is for the Solomon Island earthquake, and using all these stations, so you recognize some network in Europe as well. And here's an illustration of these multiple reverberations through the Earth's inner core. And then here you can see the travel time sections that I explained before. I showed them in color. However, here, this is for a single event, right? So the single event and all these stations on the order of thousands. And you can see beautiful observations of PK-IKP. This is a PK-IKP2, PK-IKP3, 4, 5, and so on. So you might ask yourself a question, how come that this was not observed before? Because there were active groups working on stacks of travel times and so on. And if you're curious about this, I can come back after the talk to discuss this, why I think this is observed so beautifully for the first time. And to convince you, these are different events, right? So we observe it on multiple events and different configurations of stations and receiver and sources. And you can see here examples of these multiple ricochet waves through the Earth's center. And then again, by performing a classical analysis, so for example here, the travel time or differential travel times between PKIKP2 and PKIKP4, you can see how beautifully similar these waveforms are, even though they travel through the Earth multiple times, and each passage through the from one side of the Earth to another takes about 20 minutes, right? So you can see how beautifully preserved the shape of the waveforms of these ricochet waves. And when we again perform the same analysis as before with the antipodal PKIKP, we were able to confirm that the slowest direction of propagation in the inner core for these very antipodal waves is at these angles, as these oblique angles in comparison with the rest of the inner core. Okay, so now I want you to look at how the PKIKP waves, again in a high frequency approximation, see the inner core. And here the red dots are large earthquakes and green dots are stations. This is the inner core, and you can see here how this coverage looks. So this is a zoom inner core. You can see in the northern part we have a pretty good coverage because of the dense networks, whereas in the southern sections here we have pretty huge gaps in the coverage. And you often don't realize when you look in 2D how bad that coverage really is in the southern part or in the southern hemisphere. And here are just some the color of the ray paths means a bit faster or a bit slower than the average. And I really don't have time to go into details about the inner core itself, but this is really just to illustrate you the what brings us to the Coda correlation, right? This coverage that is imperfect, and it's probably there to stay imperfect. And this is because the largest earthquakes happen in the subduction zones that we can use to study the deep Earth. The large enough to survive the passages through the center of the Earth. They happen in the subduction zones that are confined within the equatorial zone. Right? So most likely we will never have large events in the polar regions at the extreme latitudes that we can utilize to study the anisotropy of the inner core or some other properties, not to mention 3D structure of the inner core and so on. Okay, so my definition of Coda is slightly simpler because I often give this talk to a wide audience, and I like to compare it with music, right? Because many of you here are musicians, and you will know that the later part of the composition is where things are resolved, right? But quite differently in seismology, this part of the late part was often not used, right? Not used because we didn't know really how to use it to understand the Earth. And really, when you look at this, it looks random when you look at the waveforms. So in the rest of this talk, so this is really what I mean by Coda, the late Coda. So here we cut everything from 3 hours and later. And this part we throw away, right? It's completely opposite. This part we throw away, this part that's shown in red, we will keep in our analysis. Secondly, you know what the correlation is. And here I have a very simple example of simplified waveform. You know that seismograms are much more complex than that. But the bottom line is that you can utilize the similarity between the waveforms. And this becomes really our tool. That similarity, as you will see, becomes more prominent than the weak signals themselves. So the similarity between weak signals, which we can express mathematically between 0 and 1 or between -1 and 1. And then finally, I will dissect this global correlogram. And no one has done it yet, so I will take this opportunity to there are many students here, and maybe some of you are not familiar with this work. I will explain this global correlogram in detail. And of course, all of this stands on the shoulders of these, pioneering work that when we started working on this back in 2017, 2018, this is really what the situation was. There were many papers, and one of them is here by Pierre, that I like to use in my talk to demonstrate what was really our motivation to work on this. So again, I showed this. These are the classical travel time sections. And this is the figure from Boué and others. And you can see here seismically quiet days. So you can see the features in the global correlogram that look quite similar to the travel time sections. And of course, it was tempting for many people to to use these to interpret some structures of the deep earth and so on. But when you look at the days without earthquakes, the days with earthquakes here, you can see that there's a plethora of some really complex features that we don't understand. And some of them arrive before P waves. They have traditionally, they've been called spurious phases. And you can see they're quite strong, right? But if these are really reconstructed body waves, they shouldn't be there because they arrive before P waves. So physically, there's no explanation for something like this. And this, before I go into explaining some of these existence of the spurious phases or features, I just want to tell you that we benchmark everything we do here with numerical simulations, and here's an example for AXISM. This is a global network of stations and a global network and global observations of earthquakes. And I showed you already with Son's work on the autocorrelation, this was a natural step to try the global correlation from going from Antarctica to the global scale. And here I just want to demonstrate how this global correlogram is constructed. So how it really works in practice. And I chose two stations in Australia that are 15 degrees apart. So angular distance or interstation distance is 15 degrees. Australia is surrounded by these large earthquakes. So then you go and measure the cross correlation. I will come back to this period later, but we filter everything between 15 and 50 seconds. So you can think of this, the regime here is somewhere between the high frequency body waves that are used to construct 1D models of the Earth, like AK-135, and long period waves above 100 seconds that are used for normal mode seismology. So as you can see here, when you do that, you obtain some similarity between the waveforms for these two stations. And if you do it for many station pairs that are in the same distance bin, then you obtain even more features here when you stack them together, right? And you can then use the positive part of this correlation. You paint it in blue, and the negative part you paint in red. And you show it here as a strip on this two-dimensional representation between 15 and 16 degrees, right? So this is based on the data processing, so you get this strip here. Then you probably know what comes next. Next is the combination of everything that we find. And we then stack all of them in this two-dimensional representation. Again, on the horizontal axis, you have interstation distance expressed in degrees from 0 to 180. And here you have up to almost 2 hours after the origin time, all the features that we observed by this process. So this is what we refer to as a global correlogram. And yes? This is from many earthquakes. So when we started this research, we focused on about 250 events that are larger than magnitude 6.8. Yes. Yes, we'll come to that. Yeah, thank you. So this is how the global correlogram is constructed. And in particular, I will now focus on some of the features here, that some of them we intuitively understand, especially some of the positive slowness features that look the same as in the travel time sections. But one of these that's really prominent here in the lower left corner, as shown here. So you can see now we are between 0 and 20 minutes, right? So this is a zoom on the correlogram in the lower left section. And this is where we would expect P waves if they are reconstructed through this process. And then everything else here arrives before P waves, and in particular this feature. So note that I now don't refer to these as phases. I refer to them as features. And this particular feature here, I will focus on it to try to explain everything in this correlogram that you observe. So this is really what attracted our attention. That they were not explained, and so how they are formed through this process of global correlogram making. So imagine, or you don't have to imagine, the core mental boundary is real, right? It's the sharpest boundary within the Earth. It's even sharper than the Earth's surface. In particular, when you consider the density contrast. So transition from the liquid iron molten core to the silicate mantle. It's really strong, right? And I'm emphasizing that because this was a critical thing to recognize, that this boundary here is responsible for many of the features that you will see. So imagine the P wave field arriving from some teleseismic event and hitting the core mental boundary from below like this. And then you can imagine many points at the core mental boundary where there will be a transition of energy, for example, from P waves to S waves, or just refraction of P waves and so on. And you know that, as I mentioned, there's energy partitioning, and you can imagine that at this particular point here, you will have the P waves that continue as P waves and are observed on this receiver R2, and then you have S waves that are converted at the CMB, and they are observed as S waves here. You compute the cross correlation between these two records, and this is what you get, right? So going back to the really basic physics principle, you can think about Huygens principle, right? Where each point on this core mental boundary represents a new point, and it's a new source of energy. So if you repeat this exercise, right, for any point on the core mental boundary, you could create cross-correlation functions like this. And when you stack them together, you can see that most of it destructively interferes, right? It disappears on this stack. But what really constructively contributes to this peak in the stack cross correlation is this part here, and this part here corresponds to the so-called stationary points at the core mental boundary. They're stationary in the sense that if you imagine P waves leaving from these points to the surface, they would arrive at the surface with the same slowness. And when you measure the cross correlation of the same slowness, you can intuitively understand why you will see the peak in the cross correlation there, because those two waveforms are going to be most similar for this particular scenario. And you can see that these contributions, right, from the core mental boundary for these 2 points gives rise to the peak in the cross correlation function. You can now repeat this experiment for any interstation distance on the Earth's surface. So this is this particular one. But if you do it for many others, then you get this synthetic sort of correlogram or cross correlation sections where you can follow the peak for the different interstation distance all the way to the 0 where the autocorrelation is. And you can see here, again, remember we are between 15 and 50 seconds, and you can see that you can even measure the slowness of this. And when you compare it with the observed correlogram, this is how it looks, right? So I hope I convince you in this particular example that this is how we can form this, the feature that we see that arrives, right, before P waves. Remember, we are in the mathematical space here. So the correlogram is not, it's a stack of mathematical functions, right? So this particular feature here represents what you get due to the similarity of P and S waves crossing from the core mental boundary to the surface. And if you think about the ray theory and the high frequency approximation, again, you can think of these two receivers on the surface, R1 and R2, and you can think of an earthquake that happens here, for example. And if it happens so that the the reflection at the core mental boundary is exactly such that these waves arrive with the same slowness to R1 and R2, you're going to observe the peak in the correlation function. But it also means that any other event, right, with this sort of the family of legs through the Earth, if you want, but with these two in common, will also contribute to the peak in the correlation function, right, that we see here. And again, this is the why we call this CSCP, because little c here stands for the core, and then again, the time difference between S and P waves will give rise to this particular feature. This was the turning point when we realized that not only these spurious features, but pretty much everything else that we see here can be explained by the same logics. And here's an example of PKP waves, which now you notice that I call them PKP star. So PKP star here is to make a distinction between PKP waves in the direct seismic wave field and the PKP feature that we observe due to the time differences of multiply reverberating waves many hours after large earthquakes that contribute to this PKP, right? So that we call it in this particular paper, and later we call it star, right? So PKP star, and you can see here an illustration. So imagine the source here, and the PCP waves bouncing off the core mental boundary, observing at R1, and then part of it continues as a PKP waves to the core, and it's observed at R2. So you have PCP and PCP PKP. So the time difference between them is going to give you something that looks like a PKP, right, on this particular global correlogram. Okay, so there's another slide that I have here to illustrate how the PKP could be formed, or some PKP star. So imagine here again, so you have PCP PKP, or you can have something like this. One part goes as a PKP and then PCP to R2. That will also contribute to the PKP star, right? And there are many other, depending how far you go after the origin time, many other waves that will contribute to this formation of the PKP star. So again, you know, this is when we realize that we have, in a way, a new paradigm that we can use to now look at the certain parts of the Earth's interior that are maybe not sampled well by the direct or ballistic waves. But here we have a new tool that if we understand how these features are formed, we can use it in a smart way to infer the properties of the Earth. And that's why I call it here a new paradigm. But before I go to show you some applications, I want to draw your attention to this. This is a little bit later, so this is about 2 years or after we started working on this, where we realized that, wait a second, we don't need many earthquakes to do this. If we can find a single event, right, single event that sends the energy, like in those examples that I showed you, where you have ricochet waves, right? If we can find events like that, then we are in the business, right? Because we can use that single event as a fingerprint, right, of the Earth. It illuminates the Earth, again, many hours after the origin time in a unique way. And if we understand the kernels of these reverberating waves, we can use it to illuminate the Earth. And really, this search here confirmed. So these are the large events from the catalog, and you can see here in the gray are all events that didn't produce a noticeable correlogram when we use a single event. And everything that's in color here are the events that really produce a nice, beautiful correlogram. And here is one example. So this particular event, I think from the Solomon Islands, and you can see that it produces many of the features that we saw before when I showed you how the correlogram is formed. What you can also see is that the source time function of this event is quite simple, right? It's shown here. And here, if you look at, this is a quality A, so we found about 10 to 12 events, and this is quality B. So if you look at these, you recognize that one thing in common that they have is really the magnitude. So all of them are larger than magnitude 7, but it's also focal mechanisms, right? And that shouldn't be surprising to us, because these reverse and the normal mechanisms really efficiently radiate the energy down, and so that it can reverberate from the internal boundaries. Okay, and in the interest of the applications that I will show, here is an example of the so-called I2 star. This is now antipodal PKIKP, PKIKP. And you can see here, this is a classical, just the ray path of a PKIKP, whereas this is I2 star, right? So this would be an equivalent in this mathematical wave field. If you look at how the I2 star can be formed, and you can see all these different contributions. And the reason I'm showing this is just to demonstrate. I said some people at the beginning jumped very quickly into using some of these features in the mode of Green's functions to probe, for example, the inner core and things like that. But if you look at this here, this is a synthetic experiment. And what we do here is we move. So the receivers are all at the same distance, and all we do is move sources around, right? So, and if you do that, you can see here the travel time variation of this PKIKP, PKIKP, or I2 star, depending on the position of the source. And you can see here that you can get up to about 5 seconds difference if you stack all of these sources together without really noticing where they are in comparison with the stationary point, right? The stationary point in this sense means that, that it would produce the travel time that's exactly what we would expect from the travel time, the ray theory, right? So you can see how the cross correlation function varies. And also, in the interest of anticipating some questions from the audience, I will just briefly show here, this is from our review paper on this topic. So we repeated some of these correlogram exercises, but now with a much more rigorous definition of what we consider a quiet time, right? So that means that there are no days of a year where there are no earthquakes, right? There are always earthquakes. There's always seismicity. For example, in Australia, we have subduction zones surrounding the continent. There's always magnitude 5.5 or even 6 somewhere in that. So by trying to really be picky about what we select, right, you can see that the only thing that survives in the quiet time is really the surface waves, right, for this particular time period that we use. Another thing is dependence on the time after origin. So you can see here, really in this particular period, between 15 and 50 seconds, nothing here in the first 3 hours, or nothing that looks usable. And then here you have between 3 and 6 hours and 6 and 9 hours, again, the multiplicity of the features that we can use. And this is you can see how they slowly start fading away as you move away from the origin time. Another thing is the dependence of magnitude. So clearly you can see that we can only utilize for this really the large earthquakes, with some exceptions here. If you look at, we can talk about what this is. So this might be due to the microseisms that occur worldwide. But you can see here a clear dependence on the magnitude, that we really need large magnitudes to be able to do this. And finally, the question was about the mechanism type. So again, you can see clearly that normal and thrust events produce the multiplicity of features. Again, this shouldn't be taking into consideration the radiation pattern. This shouldn't be a surprise when it comes to the P waves. And I should say that everything we do here is on the vertical components, right? And so you can see why the mechanism type is important. Okay, so this brings me to the last part, and to show you some applications of this. How much time do we have for this? 15 minutes, okay, so that's plenty. So to leave some time for maybe a couple of questions. There are many applications, and today I will actually I will focus on some of our current work and some of the more prominent results that I think are worth showing in this symposium. But before I do that, I have maybe 2 minutes to spend on the inner core of the Earth, and to really demonstrate why this is again important, why the Coda correlation makes a really great complement to everything we know about the inner core. And we do know a lot, right? The inner core is small on the planetary scale. It's less than 1% of the volume. And there has been a lot of research on, particularly from seismological perspective, enough for me to write a book on the inner core. It's a very thin, it's not thick. But if I had to write the second edition, it would be maybe 2 times thicker. And that kind of shows you how quickly we make progress in the last 5 years or the last 10 years on this topic. Of course, maybe there are not many geodynamicists in the audience, but we all know, and if we have to make some societal impact of the inner core, when we write proposals, we always go with the magnetic field, right? Because the magnetic field is a direct consequence of the processes, dynamic processes within the liquid outer core. And particularly there's a latent heat when you go from the solidification, when you have a solidification of the inner core in some point of the Earth's history, when the temperature drops down enough for this solidification to happen. And because of this compositional convection and latent heat, you have a geodynamo, right? So this is what we know about the inner core. We also speculate about the chemical composition, but it's an iron-nickel alloy with some light elements that are shown here. There are many more things that we don't know about the inner core, right? So if I ask a quick question, what color is the inner core? What color? Like if you were in your mind able to dismantle the Earth, what would you see? No. We think it's white. And why white? Because the temperature, and again, the temperature, some of the largest uncertainties, right, in the science in general, not just in the inner core science, is the temperature of the inner core, but somewhere between 5,000 and 7,000 degrees of Kelvins. So that puts you closer to the temperature of the sun's surface, and it's white. So at least for a moment, it would be white, right? Because it would quickly go down, right? But all of these, and I don't want to talk about this too much, but if you think about viscosity, the order of magnitude of uncertainty goes from 0 to 10 to the 22 Pascal seconds. So that gives you an idea, 22 orders of magnitude uncertainty. It's some of the really largest uncertainty. That's what makes this field mysterious, and we are still in the discovery stage, and this is really fun about it. So, but one of the specific question is the shear properties of the inner core, Because shear properties, we don't have, at least you will see, we don't have direct measurements of that through the existence of shear waves. Or at least the community is split on this, some of these observations that were made. So these, these are the missing, missing pieces of puzzle, if you want, to understand the structure of the inner core, to understand what is the stable phase of iron, for example, and so on. Here I show you, and most of you will know, this is PKIKP, this is PKJKP. So PKJKP would be the simplest expression of shear energy in the inner core. If we could observe PKJKP waves, right? Because shear waves do not propagate through liquids, right? So if you have this observation, then you know that you have a solid inner core. And as I said before, the community was split on this. There were about 10 papers in the history of seismology from the time that the Francis Birch proposed that what Inge Lehmann discovered in 1936 was really that phase transition from liquid to solid iron. In this work, and as I said, J-waves have been elusive. So can we use Coda correlation and everything that I showed you before to look at the shear waves in the inner core? And this is what Son and I were thinking back then in 2018. If we can conduct a simple synthetic experiment where we change the shear wave speed with respect to Prem, and we compute the synthetic correlogram with slightly different properties of shear wave speed in the inner core every time. Can we see any change in the global correlogram? Because if we do, if we see the change, that means we are sensitive to that little change in the shear wave speed in the inner core, right? Of course, inner core is small, right? Inner core is less than 1% of volume. So you intuitively know that if you do some fine tuning in the inner core, that you shouldn't be able to see much change in this correlogram. But look what happens, right? So when we change the shear wave speed here from -15 to 20% with respect to the Prem, of course, as expected, we see that not much is changing, but there are some features that go up and down, in particular here in the window B. So you can see how this cusp of energy sort of goes up and down, right? And so we figured, to make a long story short, that this similarity or this peak in the cross correlation is due to the similarity of PKIKP waves and PKJKP waves. And indeed, if you measure the slowness and so on, it confirms that this peak that we are observing is due to the change of shear wave speed, right? So we do have a direct tool to now look at the shear wave composition of the inner core. And when we compared our synthetic correlogram with some fine tuning and the grid search of shear wave speed with the observation, we were able to establish that the shear wave speed that we are observing is 2.5% smaller than in what Prem predicts. Now, for some, this might be a surprise. For others, not, because Prem, as I said, it's constructed with a long period waves, and it should always be taken with a grain of salt, because they were not really, and the normal modes are not sensitive all the way to the center, and it's therefore not surprising that some modification of Prem is due to the imperfection of our observations before. And most recently, we refined this with PhD student Tuani, and I think Son had a poster that some of you have seen how we refined this measurement. But this time, instead of PKIKP, and PKJKP, we were able to use a direct similarity between PKIKP and PKJKP. And the reason for that is that we got a much clearer correlograms due to the way how we select the data, right? And one thing that I already mentioned is the focal mechanisms. So here, with the careful selection of just a reverse and normal mechanism as opposed to mixing everything, and also with the careful selection of receiver pairs and the source, so that all of them are along the great circle planes and constructively contribute to the cross correlation, we were able to really make much clearer correlograms and these observations. The next is we use the global correlograms now to basically construct a new model of the Earth based on just this period range between 15 and 50 seconds. And for that we used 71 features that we were able to catalog, first to identify how they are formed and then to catalog. And you can see here comparisons of when we constructed our new model called CCREM, how CCREM fits here in the last column, some of these features. So for example, this is PCP star in the top row, and this is K4 star. This is a multiple PKP in the outer core, if you want, equivalent. And you can see that CCRM, of course, it's based on this data. It can fit these features, and this is, for example, how PREM sees some of them, and AK135, and this is EK137, which is just a new version of AK135. And to make a long story short, this new model, especially in the outer core, kind of agrees with the individual studies that are used both by body waves and normal modes. In particular, in the upper part of the outer core, you can see the velocity reduction with respect to PREM, and also in the base of the outer core. So near the inner core boundary, you can see these reductions. And that was not surprising. But what I will show you now is a really surprising observation, which I consider the first order observation in seismology. At least the same order of magnitude importance as our first realization that the inner core is anisotropic. And I showed you already that in that case you have about 5 or 6 seconds difference between equatorial and the polar parts. So what we did here, we divided our stations, our global stations here, to the polar and the equatorial part. So everything that's further away from 35 degrees is polar, minus 35 to the south and 35 to the north, and everything else is equatorial. And then we perform exactly the same analysis using all these events and stations. Based on this polar group, we define or we construct this correlogram. Based on the equatorial group, we construct this correlogram. You can see they look very similar. It is almost impossible to make any differences between the two. But look what happens when we look closer in these two. This is now the feature that is PCP star, SCS star, CSCP, which you are now familiar with. And these are the features that are really mostly sensitive to the structure in the mantle of the Earth. You can see that when you compare polar and equatorial groups, you see no difference between the waveforms, right? Between the between the cross correlations. However, when you look at these features, which are sensitive to the outer core structure, you start seeing this huge difference. I mean, when I say huge, it's on the order of 5 to 6 seconds, which is really huge enough to be called huge in this type of business, right? So this is the first order observation that I refer to, that there is something that's causing these delays or advance between the polar and the equatorial. And to make a long story short, when we look at the different models of the outer core that can produce this, here is the model with the so-called Taylor or tangent cylinder. Here is the model with the reductions of velocity near the base and near the top. And you can see that in both cases we don't get this disparity or the difference between polar and equatorial. However, when we construct a model that looks like this, and we did try many models that are in between these two. So basically you can think of this one and the tangent cylinder one, and many models in between, including those that have something on the caps, We tested the mantle structure, including subduction zones, including the core mantle boundary, ultra-low velocity zones, LLSVPs, and so on. Everything that we can think of, nothing produces this difference except this kind of shape. In mathematics, it's called torus. So we propose that the outer core structure is actually defined by this sort of torus difference. In that, in the equatorial zone, in the outer core, we have down to 1.8% reduction with respect to the prem. This work is still being revised and so on, so it's not published yet. So just to then conclude with these advances, here is what we are doing at the moment. We're trying to compute the kernels of the Coda correlation. And here's an example if it works. So this one is how the propagation of the Coda correlation wavefield looks here for this 2 hours. For this we use adjoint method where we have to calculate the forward wavefield and the adjoint wavefield. And the hope is that by doing this, and particularly finding the events that have this really expressed P star, which now has the slowness that really travels through the mantle, you can see the mantle, that you can actually perform tomography in the same way that the classical tomography works, just with the Coda correlation. And here is again an example of how the travel time kernels look for this particular time window here. And you can see some of the features that we already marked here. And if I run this, you will recognize some of the, this is again how the Earth structure responds to the changes. So how the travel time responds to the changes in the Earth structure. And you can recognize some features that look like PKP, and so on, that are from this bunch of bunch of features. Yeah, so the idea here is that when it comes to the comparison of observations and predictions, we'll be able to use correlograms from individual earthquakes, because this is a 3D structure. Everything I showed so far is spherically averaged. So the idea here is to really perform tomography with individual events. And finally, you might wonder, okay, so everything we did here is with the thousands of receivers on the Earth's surface. So how on earth you do it for Mars, when you have a single InSight seismometer, and we have seen some talk about this, and in such an environment where we have a single receiver and only about 10 or 20 low-frequency earthquakes that could be, Marsquakes that could be compared with earthquakes, how can we utilize them? So luckily for us also, during this time when we submitted this paper, there were impacts. And impacts are observed with orbital cameras. So you can basically use impacts as a ground-truth event. So you know location really well for impacts. For long-frequency Marsquakes, it's a little bit more disputable. How well do we know the locations, right? But you can imagine that we have about on the order of 20 events and one receiver that we can use. So again, using the reciprocity theorem, the mathematical trickery here, we can replace. So our receiver, our our InSight becomes a virtual source, and all Marsquakes that we observed and meteorite impacts become virtual receivers. So by doing this, we have first illustrated the feasibility. Can we do it for the Earth, right? And this is really, again, comes down to this data selection. If you use all data that you have, right? So now I'm talking about inter-source correlation instead of inter-receiver. So if you do it, theoretically, you would expect to see the same thing. But if you mix all data, this is what you get. So you see nothing here. After the selections, and again, the careful selections in respect to the source mechanism and also in respect to the great circle path, we get this, right? Which is exactly equivalent to what we had before. So this is inter-source global correlations. And then we did it for a single station, just to show the feasibility. This is a station Nana in Peru, and we already know this station, Pinon Flat. And you can see that for these two individual stations, and again for many sources, we obtain the global correlograms that are now familiar to you from the previous slides. And when we applied this to Mars, we were able to look at some of the features that are sensitive to the Mars core, right? So one of them is SES star, one of them is CSCP, which I already explained before. And by comparing observations with our synthetics, we were able to deduct the radius of the Mars core, which is 1,812 kilometers, which I think I had somewhere, but it's not shown here. So here, it's 1812 plus minus 20 kilometers. That was our estimate for the size of the radius of the Mars core. So we claim that basically with this tool, if you have a planet which is tectonically active, or at least you have meteorite impacts, you can use this even if you have a single receiver to scan for the presence of the core, because these features are going to be sensitive to the core. And this just shows the comparison of the global coverage that you achieve with, this is the inter-source correlation. So the lighter colors here means better coverage. So if you compare this with, for example, inter-receiver correlation coverage, you can see the advantage. And this has to do really with the configuration of receivers and sources on the Earth's surface. And then finally, this is a classical seismology with the receiver source pairs. So you can see that in both cases, inter-source correlation has the largest potential to really achieve the volumetric coverage of the Earth. And I don't want to spend too much time on this. I just want to say that when it comes to the Earth, we really started using correlation wavefield, which I hope I demonstrated. But when it comes to the Mars, we really just scratched the surface with the correlation wavefield. The Moon is about to come, and I'm proud to say that the Australian Space Agency and in particular the space industry is now thinking about landing on the Moon as well, to join all other countries. So there's at least 5 to 6 countries that will land on the Moon in the next 2 years or so. And this particular one on the farther side of the Moon. And we hope to be able to use the correlation wavefield in the same mode that I demonstrated to look for the presence of the lunar core and to characterize it further. The same for Mars. We have already used correlation wavefield, but the Mars core size and the character still remain mysterious. Particularly in terms of why Mars doesn't have the magnetic field, and it used to have it, but it ceased to exist. Okay, so the first take-home message that I want to send is that you have to celebrate successes, and I hope I demonstrated that we had some successes in the past years. So what I do for my students, I cook, and I pair each dish with the wine. These days, my wife cooks. But the bottom line is that you have to celebrate successes, and that I really like to convey this message to both students and supervisors. In terms of the conclusions of this talk, I hope I demonstrated that the at least earthquake Coda correlation wavefield is a mathematical manifestation of the seismic wavefield, and that in the features in the late earthquake Coda correlograms are not reconstructed body waves, but they arise, if I should use this term, due to the similarity of reverberating seismic waves. And in particular, when I showed you a single earthquake, I hope that demonstrates this principle, right? You have single earthquake, you get a correlogram that's basically you can illuminate the Earth based on this principle of reverberating seismic waves many hours after the origin time. And then I show you some applications here. They're not limited to the Earth, but hopefully to the other planets. So maybe this one that I have in bold, the similarity between the two weak signals is more prominent than the weak signals themselves. And this is really what if in retrospect, I think this is what we capitalized on, this particular principle. Especially, I hope I demonstrated it with the J waves in the inner core. So, while we are mapping the Earth's surface, we are still in the discovery stage when it comes to the deep Earth, and it's still mysterious and it's exciting, and I think it will keep being exciting and fascinate us really in the next few decades at least to come. So thank you very much for your attention.